All right, this is where I want to start because we do need to review this. So in this video, what I want to do is I want to make sure that we go over the chain rule and applications of the chain rule. So we know F and G are differentiable, but more importantly, F is differentiable at G. In fact, usually we do it for a point, but so if I have this composition and I want to take its derivative, it's the derivative of the outside function, leaving the inside function alone, times the derivative of the inside function. So let's look at a few things. So our power rule for normal powers is this. Our generalized power rule, where u is a differentiable function of x, starts out the same. There's the outside derivative times du dx. Okay? And we can keep going. So for example, if I have the derivative of 3x minus 4 to the 20th power, I start with the generalized power rule. So that's 20 times the inside function to 1 less degree times the derivative of the inside function is 3. Now, oops, I clean this up. And there we go. Now, you should remember that the derivative of sine x is cosine x. So the derivative, its chain rule variant, of sine of u, sine of stuff, is the cosine of the stuff, derivative stuff. So if I have the sine of e to the x, well, that will be cosine e to the x times the derivative with respect to x of e to the x, which is e to the x cosine of e to the x. And as you can see, we can keep going. Now, there are a few applications of the chain rule. Okay, let's write that down. Applications of chain rule. We have the derivative of the inverse function theorem. We have related rates. We have implicit derivatives. Now, when I'm dealing with inverse functions and finding inverse function rules, I tend to like to use that. Because implicit derivatives, I think, are easier for many students versus the derivative of the inverse function theorem, which can get really messy with notation. But you guys are smart, so I know you can figure it out. So let me make up a relation. xy squared plus 2x squared plus 3y squared is 12. So the derivative with respect to x of the left-hand side, oops, I almost copied that down wrong. That would have been very tragic. Y squared plus 2x squared. Okay, the derivative of a sum is the sum of the derivatives. Okay, this right here, we start with a product rule. So the derivative of x is 1 times y squared plus x times the derivative of y squared is 2y, and then don't forget the chain rule. Plus 4x plus 6y, don't forget the chain rule, is nothing. Now, I'm going to gather my dy dx's on the left-hand side. So that will be 2xy plus 6y. And now I can use my pun, do you see why? And I bring the other materials to the right-hand side. So dy dx is the opposite of y squared plus 4x divided by 2 times xy. You know what? I should have factored that y out. I didn't, but let's go ahead and we'll just fix it on the next line. There you go. But now, let's look at implicit derivatives. Hi, Roxy, how are you? And inverse functions. Okay, so first of all, you need to remember that a function's invertible. That means it has an inverse function if it's strictly one-to-one. What's that mean, Mr. Isaac? It's either strictly increasing or strictly decreasing. So if I want the derivative of the natural log of x, I'm going to start with y is equal to the natural log of x. Well, that says that e to the y is x. I'm going to use this relation in a second, so don't lose. You never want to mess with that. Now you come over here and take the derivative with respect to x of both sides by the chain rule. You get that on the left-hand side, and I hope that you know that the derivative of x with respect to itself is 1. So dy dx is 1 over e to the y, but e to the y was x. So you now know that the derivative with respect to x of ln x is 1 over x. It's chain rule variant. The derivative with respect to x of the natural log of stuff is 1 over stuff, derivative of stuff. Now, when you're dealing with logarithms, it's fortuitous to simplify them in the beginning because it'll make simplifying them in the end a lot nicer. Let's, we've done the other ones in class. You know what? How would I take the derivative of x to the 2x? Guess what? It's going to be implicit derivatives and logarithms. So I start by let y be x to the 2 to the x. So the natural log of y is equal to the natural log of x to the 2x power. However, using log properties, I can do that. Now I'm going to take the derivative with respect to x of both sides. There is another way to do this, but if you're not strong with compositions, it can be insane. On this left-hand side, 1 over stuff, the derivative of the stuff with respect to x. On the right-hand side, I have 2 times. 2 is a scalar, that's why I factored it out. I have a product rule, 1 times ln x plus x times 1 over x. So dy dx is equal to 2y times the quantity ln x plus 1. Now be careful that you realize that this is the only thing in the argument. What was y? Well, you come back up here, and hey, there it is. So 2 times x to the 2x times the natural log of x plus 1. Isn't that cool? That is just so cool. Now let's go back and let's look at that. Let's see what we've gone through so far. We've talked about implicit derivatives. We've talked about using implicit derivatives to do the derivatives of an inverse function. But there is an inverse function theorem. Now, folks, it's a lot easier, and a lot of people make this way too hard. So normally, how you compose 2 functions, the order matters, except for when the 2 functions are inverse functions of each other. Then the order doesn't matter. But typically, I'm going to let g be f inverse to make the notation nicer here. If I take the derivative with respect to x of both sides, by the chain rule, I get f prime of g of x times g prime of x on the left-hand side. On the right-hand side, I get 1. So really, all you need to know is right here. Because what that is saying is the product of 2 slopes of tangent lines, one being on the function and one being on the inverse function at the correct corresponding point, is always 1. That means they're reciprocals. So if you know that f is invertible, and you know that 2, 7 is a point on f, that only happens if 7, 2 is a point on its inverse. If you know that f prime of x is 6, then you know that 1/6 is f prime. Oh, you know what? That's not f prime of x, Mr. Isaac. We need to put a point in there. Let's fix that. F prime of 2, excuse me, please forgive me. Now remember, 2 gets mapped to 7, so over here, the inverse function's derivative, which I called g prime of 7 is 1/6. But Mr. Isaac, okay, let's do it the old-fashioned way. We come up here, we take this derivative here, we'll call this line plus, and this is plus 1. But we're going to evaluate that at our point. So we have f prime of g of x times g prime of x is 1. Now we're interested when x is 6 because we want to be, oh wait, I put the wrong number in there, not 6. Wake up, Mr. Isaac. Let me see my point. Where's my point 2? No, not 2, 7. Hey, come on, select the pencil. Okay, now watch this. But g of 7 is 2. So this is f prime of 2 times g prime of 7 is 1. This is the slope of the tangent line for f of x. We said that was 6. 6 times the slope of the tangent line on the inverse function at x equals 7 is 1. Therefore, g prime of 7 is 1/6. See, they tell you the same thing. You just need to take your time and go on. Now, I want to keep this for both my classes, and right now, AB kids, you've only done this and this. BC kids, you have related rates. So you know you'll be taking word problems, writing equations, and stuff like that. You got this?